Today we'll be covering the power rule and the sum and difference rule with lots of examples and a proof at the end of the power rule for positive integers. Um, it works for non-positive integers as well. This definition is going to be the power rule. Let f of x equal c times x to the n, where c is a real number and n is a non-zero real number. Non-zero is key here, okay? Then the derivative in terms of x of f of x is equal to f prime of x, right? This is the shorthand we use. They mean the same thing. I prefer using this notation for shortness and this one for clarity. Equal to n times c times x to the power of n minus 1. Not ncx to the n and then minus 1 out here. Okay, don't do that. N minus 1 up here, like normal civilized humans. Okay, we're gonna do so many examples. It's gonna be so fun. Ready? For example, f of x is equal to x to the fourth, where c is equal to 1, n is equal to 4, and that means f prime of x is equal to 4 times 1 times x to the 4 minus 1, which is 4x to the third. Easy money. How about we say, oh, well, what if f of x is equal to 13x to the seventh? F prime of x is going to be 13 times 7 times, oopsies, x to the sixth, because n is equal to 7, n minus 1 is 6, c is equal to 13. Oh, but Amanda, what if we have negative numbers? That's fine. F of x. Why did this get loud? Please hold. Okay, sorry, figured it out. Let's say f of x is equal to negative 5x squared. That's fine. N is equal to 2. C is equal to negative 5. F prime x. Please, these are not the same. Don't write them as equal. Okay. F prime x. I'm written like that or like that. Okay. Is equal to negative 5 times 2x to the first, which is negative 10x to the first. We could do this all day. Ready? Oh, what if the exponent is negative? That's cool. Let's say this is 7x to the negative 8. N is equal to negative 8. And it's non-zero. C is equal to 7. That means f prime x is equal to negative 8 times 7x to the negative 9. Ooh, fancy, right? Oh, well, what if, um, it's a weird number. Oh, ready? 1x to the root 3. N is equal to root 3. N minus 1 is equal to root 3 minus 1. Minus 1 out here, okay, folks? Not in here. Out here. And c is equal to 1, just so it's easy for you to see. Then you say, oh yeah, then f prime x is root 3 x, that's a 3 I swear, to the root 3 minus 1. Oh, but what if the coefficient's weird? That's cool too. F of x is equal to root 3x to the 7th. Again, n is equal to 7, c is equal to root 3. F prime x is equal to 7 root 3 x to the 6th. Oh, what if I throw some pies in there, right? Pi is 3.14. Please don't write that out. Because if you do, I'll make you write the whole thing out. All the digits of pi, okay? F of x is equal to x to the pi. N is equal to pi. C is equal to a magical hidden 1 right here, right? I'm just not going to write it anymore. Mad work. F prime x is going to equal pi x to the pi minus 1. Again, pi minus 1 written like that, okay? I'm going to gently insist that you have parentheses, okay? Oh, what if f of x is equal to x to the pi squared? Easy money. F prime of x is going to be pi squared, like that, x to the pi squared minus 1, like that. But Amanda, what if we have fractions yet? What if we have fractions? That's fine. F of x is equal to 1/3 x to the 7th. That's cool. F prime x is equal to 7/3, 7 times 1/3, x to the 6th. But Amanda, what if, what if, what if, I'm running out of what ifs. Oh, f of x is equal to, um, 7x. Okay, this one's a little fun, right? C is equal to 7, n is equal to 1, n minus 1 is equal to 0. F prime x is equal to 7 times 1 times x to the 1 minus 1, right? Which is 7x to the 0, which is not equal to 0. Do not do that, okay? X to the 0 is equal to 1. If you don't know why, please get back to your exponents and then we can come back to this, okay? Just 7 times 1, which is 7, which like vibes-wise makes sense, right? Because this is saying like y equals 7x plus 0, right? And a derivative is a slope function, right? M is equal to 7. So y prime should equal to 7. Yeah? But what if what other what ifs can I cook? Oh, what if I have f f of x is equal to x to the 5/3? Shoot, that's okay. F of x is equal to 5/3, x to the 5/3 minus 1, right? Which is equal to 5/3 x to the 2/3. But um what if f of x is equal to x to the 1/2? Then f prime of x is going to equal 1/2 x to the negative 1/2, right? Because 1/2 minus 1 is equal to negative 1/2. Right? But what if f of x is equal to um the third root of x squared? Alrighty, let's take a quick detour. Quick detour. So the kth root of some x to the p is equal to x to the p over k. Why? Consider like the square root of x, right? Root x times root x is equal to x to the first, right? Let's do a little substitution magic. Consider like, let's say that the square root of x, which I'll just write as root x, is equal to x to some power k, right? And that means root x times root x, which we know is equal to x to the first, right? Is also equal to x to the k times x to the k. We know what that is. That's x to the 2k, right? So that means these two pieces have to equal. X to the first is equal to x to the 2k. K must equal 1/2 or else these two can't equal. Therefore, root x is equal to x to the 1/2. Anyway, back to here. Once you get here, you're like, oh, this is the same as saying x to the 2/3. And then you say, oh, f prime of x is equal to 2/3 x to the 2/3 minus 1, right? Which is 2/3 x to the negative 1/3. Easy money. But wait. What if we have f of x is equal to 3x to the root 11? That's fine too, because f prime of x is going to equal 3 times root 11, x to the root 11 minus 1. Minus 1 on the outside of the square root, okay, friends? Not on the inside, on the outside. Just like that. But what if n is equal to 0, right? Because we stated that n cannot equal 0. So what happens when it is? Well, that means you have some g of x, or f, it doesn't matter, I call it g of x for differentiating it, right? Is equal to, let's say 7x to the 0, right? We know what x to the 0 is. X to the 0 is equal to 1, right? This is a linear function. In fact, it's a constant function. And what is a derivative, right? The derivative is a slope function. Okay. So that means there are a couple different ways we can look at this. One, y2 minus y1 over x2 minus x1 of all points on g of x is equal to 7 minus 7 over the first point minus the second point, which is equal to 0 over some number that's non-zero, which is equal to 0. Another way to look at it is, if you look at the function itself, right? Let's say this is 7, right? It's rise over run. Rise over, ooh, run. But your rise is 0, right? Which is going to equal 0. Another way to look at it is the limit definition. The limit as h approaches 0 of g of x plus h minus g of x all over h, right? What is g of x plus h? You plug in x plus h into here, and what do you get back? Right, you should get back 7. And the g of x is 7 as well, right? Limit h approaches 0 all over h, right? Then all of a sudden, you get 0 over h. The limit as h approaches 0. 0 divided by any number is going to equal 0. So the limit as h approaches 0 of 0 is 0. Okay, not so bad, right? What we're going to cover now is the sum and difference rule. The definition, sum, and difference. Okay, so let f of x and g of x be functions, then, or I guess, yeah, then the derivative in terms of x of f of x plus g of x is going to equal f prime of x, the derivative of the first piece, plus the derivative of that second piece. Similarly, the derivative in terms of x of f of x minus g of x, right, is going to be the derivative of the first piece minus derivative of that second piece. Easy money. Okay, now I'm going to crash course, or I'm going to go over the proof of why this works, okay? For those of you who are curious, or for this, okay? I'm not going to rewrite it. I had recorded it and then it didn't record right, so I have the thing written out. I'm not going to write it again. Okay. Okay. Where are we? Okay. So why are we even allowed to say all that, right? Ooh, don't do that. Why are we even allowed to state this claim? Let me highlight this in green. Why are we even allowed to state this claim right here, right? What I'm going to do is I'm going to prove for n greater than or equal to 1, where n has to be an integer, because I can't remember how to do it when n isn't. Okay? And I forget how to do it for when n is negative. It requires a bit of gymnastics, and I can't remember how the gymnastics work, and I don't want to torture you. Okay? So let's consider some function f of x is equal to c, some constant, times x to the power of n, right? By definition, we know that f prime of x is going to equal the limit as h approaches 0 of this f of x plus h, right? So you just have to substitute x plus h into here, right? Once you do that, then you can say minus the original f of x all over h, right? Nothing crazy. You remember for coefficients, right? You can pop them outside, right? And so what we're going to do is we're going to factor this and this to bring it here, like that, right? And then once we have that, we're going to factor that c out to make it look like this, okay? Okay, this next part is going to be binomial coefficients, okay? It follows Pascal's triangles, something, something, it's not entirely important, okay? What we do know is this piece right here, right? Actually, you know what? Let's crash course it real quick. Do you guys remember, right? X plus h to the third is the same as saying x plus h squared times x plus h, right? Which is going to give you x squared plus 2xh plus h squared, x plus h, which is going to give you x cubed plus 2x squared h plus xh squared plus x squared h plus 2xh squared plus h cubed. You guys notice there's only one term, right? With x by itself, no h. And there's only one term where it's x squared and a single h, right? Once we combine everything. Because this is going to equal x cubed plus 3x squared h plus 3xh squared plus h cubed, right? What you'll notice is x cubed is the same as x cubed h to the 0. This is x squared h to the first. This is x to the first h squared. This is technically x0 h to the third, right? What you're going to notice is that if you add these exponents up, they add up to this piece, right? 2 plus 1, 3. 1 plus 2, 3. 3 plus 0, 3, right? And then you're going to have some random coefficients living out here. It's not important what they are, okay? Okay, they're also not random. That's not the point. Because that means you can write it out like this. I'll go over piece by piece, okay? The binomial system will tell you that the first one is going to be x to the n h to the 0, because this adds up to n, the original power we're looking at, right? And then this is going to be n choose 1, and then n minus 1, x to the n minus 1, h to the first. It's not important what this is, okay? Not yet, at least. This is going to be n choose 2, x to the n minus 2. Do you see how it matches? H to the 2. You can keep doing that all the way down, right? You're going to get n choose n minus 2 times x squared times h to the n minus 2, yada, 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 right? And what you can do now is you're not going to forget this x to the n, right? We've expanded this into this monstrosity here, and you just carry that down, right? But what you're going to find is, like we mentioned earlier, there's only one term that is x to the n and no h. There's only going to be one term left over from this piece up here that is x to the n. And when you add a positive one to a negative one, you should get 0 back, right? And what that'll do is it'll bring you back down to here, right? Notice how everything here has some h's in it, at least one, right? In fact, there's only one term that has h to the first, right? Oh, and then you know that baloney, right? And then you're going to look at this. You're going to say, oh, this is just business as usual. It's just kind of long, right? We can factor out h's. They all have them, right? And we factor out those h's, right? We put the h out here, right? you'll find, oh, this becomes h to the 0 because you popped an h out. This becomes h to the 1. Da 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 da. This becomes h to the n minus 3, n minus 2, n minus 1, right? And then you can just say, oh, we have a factor of h here and a factor of h here. We just cross them out, right? And then here's the fun part. Here's the fun part. This piece can be simplified. When someone says n choose k, right, we're saying out of n items, how many groups of k size can you make, right? So for example, out of 30 students, it's how many different, to be fair, groups of one student can you make? The answer should be 30, right? There's only 30 ways to make individuals, right? It's like saying, oh, get into groups of one. There's 30 of you. How many groups am I supposed to have? Right? That's what that means. But that means n choose one. Make n groups of one. There should be n groups, right? And then h to the 0, is just h to the first, right? Or is just 1. This doesn't do anything interesting, right? Once we have this simplified down, right, we're going to write it here, right? And now all we have to do is take that limit. And there's no weird behavior here. So we just plug 0 in. This is going to be some amount of stuff, some number to times x to the whatever times. You apply the limit, that gives you 0. Stuff times 0 is 0. All of these things in between also have some kind of stuff times 0. All this stuff in between is going to be 0. This is going to be 0. This is going to be 0. Even this is 0, right? Because at the end of the day, you're looking at some coefficient times some x to whatever power times 0 to whatever power. It's just stuff times 0, and that's going to give you 0. Which means this entire chain goes to 0. The only thing left is the sky. Because if you apply a limit and there's no h, nothing happens. And that is how you are left with b times n times x to the n minus 1. And I think that's really cool. Okay. Thank you for your attention. I really appreciate it. Inshallah, the video recorded right this time.